Okay, at the end of the last video, we were talking about the situation where we've got water and vapor in a closed container. And the distinction between the molecules that are in a liquid state and those that are gas really comes down to a matter of energy. How much energy do they have? And the energy can be drawn in from the container or the room that it's in if it's hot. And so it gains a little energy and it jumps up into the vapor state. And similarly, you might have some vapor molecules that lose energy to the container or the surrounding parts of the system, and they therefore lose the energy to be in the vapor state, and they fall back into a liquid state. And eventually everything balances out, and you get this equilibrium between the vapor and the liquid, and that is said to be saturated, meaning that the air here is full of as much liquid as it can contain. And so the amount of liquid or former liquid that is becomes vapor that can be held in air depends on the temperature. So the higher the temperature, the more vapor can be held in that air, which is why on hot summer days it often feels humid. We can feel the humidity. We can feel the vapor in the air. On cold winter days, when it gets cold, the air gets dry because it cannot hold as much vapor. And so we might get chapped lips or dry, cracked hands as a result of the dryness of the air. And then pressure plays into this as well, just like temperature. So pressure and temperature are directly related. So as the temperature goes up, the pressure goes up, and as the temperature goes down, the pressure goes down. So the temperature at which water boils, we tend to think of as being a constant, 100 degrees Celsius. And essentially what's happening is when the saturated vapor pressure equals the external pressure, so the pressure we have pushing down on this container from the atmosphere. When the pressure just above that gets high enough to push back and equalize it, that's when the water begins to boil. So the temperature goes up, the pressure goes up. When the pressure finally gets up high enough to push back against the atmospheric pressure around it, the water will boil. But the thing is that the atmospheric pressure is not constant. It changes with the weather. It can also change with elevation. So, for instance, if you've ever looked on a package of macaroni and cheese, it might have directions for high elevation cooking instructions. And what it typically is you have to cook it longer, because if you are at a high elevation, let's say you live in Denver, Colorado, or any other high elevation location, there's not as much atmospheric pressure pushing down on you. What that means is that the water is going to boil at a lower temperature, and so when the water is boiling at a lower temperature, the food that's boiling in that water is not being raised to the same temperature you would normally expect. So you have to cook it longer to get the same amount of energy into it because the temperature is not as great. So I've kind of already talked about this. The humidity is something you hear about in the weather forecast. It's something that we can feel. In the summer, it's more humid. We can feel that vapor on our skin. It makes us feel hotter, actually. And in the winter, the air cannot hold the same amount of vapor. and the air gets dry, and we feel that as well with our dry skin. So relative humidity, the definition of that is the the pressure of water vapor, the amount of vapor in the air causes pressure, divided by the saturated vapor pressure. So essentially, it's saying how much vapor is in the air compared to the total amount of vapor that could possibly be held. Saturated basically means it's full. It's got all the vapor in it that it can handle. So this is if the relative humidity was 100%, we would be saying that the air is in fact saturated, that it couldn't possibly hold any more water vapor. And so changes in pressure and temperature result in weather changes. So increases in pressure can result in the fog here. You've got lower pressure at the tops of the mountain than you do in the valley. Higher pressure in the valley causes that vapor to turn into actual water droplets in the air that you can visibly see. Dew occurs overnight because of the temperature drop, and vapor in the air turns into these water molecules. And of course, rain occurs when the vapor in the clouds, when its temperature drops and it turns to water and falls to the earth as condensation. The last topic in this chapter is diffusion. So if we were to go all the way back to the beginning of this chapter, the first slide, I had that PowerPoint animation of Brownian motion, of that particle just kind of zipping around in an irregular random pattern. So the water molecules are sort of doing that. They're moving around, they're colliding with each other. And we've talked about how the temperature of the liquid is essentially just a measure of how much kinetic energy those molecules have. And so higher temperature fluids will have more kinetic energy. And the more kinetic energy the molecules have, the more quickly they will disperse some other material that's added to it, in this case food coloring. If you were to put a few drops of food coloring into a cold glass of water, it would possibly just sit there like this. And it would take a much longer time to get to this state here where it has been completely diffused throughout the water. It will get to this point much faster if the water is hotter and therefore has more kinetic energy. So if we were to look here, let's say this is like a ductwork in a heating and cooling system, and we have some area here where the air molecules are more concentrated, and over here they're less concentrated. Well, nature wants things to be in equilibrium. So these more concentrated air molecules are going to disperse or diffuse until they're evenly spread out. And so if we imagine these particles being in some sort of a tube or duct with a cross-sectional area, and that they're moving along its length some distance x, and we have region 1 here with a certain concentration, and region 2 with another concentration, we can come up with a formula to describe how quickly those molecules will diffuse and become evenly distributed. And that equation is right here. The diffusion rate is J. That's how quickly something will diffuse. It is equal to dA. A is the area. C1 and C2 are the concentrations. And X is the distance between those areas. So that just leaves D. What is D? D is what we call the diffusion constant, and it varies depending on the material. So for air, let's say the medium is air and the diffusing molecule is hydrogen. Look how quickly it diffuses compared to oxygen. Oxygen is a bigger, heavier molecule, so it's going to have a lower diffusion constant, which means it's going to have a slower diffusion rate. And then if we look at some of these other materials, in water, diffusing in water, let's just stick up here with oxygen. Oxygen in water, that's to the negative 11th, so that's a lot smaller. So that oxygen is going to diffuse in water much more slowly than it would in air. Okay, that finally brings us to the end of chapter 13. If you've got any questions, post them on the discussion board, and I'll try to remember to get some of those videos I referenced earlier posted to Blackboard as well.